Hi, my name is Josephine Nwama, and this is Physics 1, Lab 3 about black holes. So as an introduction, in Part 1, we're finding the mass of a black hole by analyzing the motion of a star, in which the gravitational force of the black hole is acting on. And in Part 2, we're calculating the initial velocity of a spaceship and necessary net forces using the calculated mass in Part 1 to visualize the trajectory of our spaceship to get it close enough to the black hole without crashing, but still being able to leave the system. So here is a preview of the brief results. Now let's see how we got there. So here are some fundamental principles that we need to understand for part 1. First off is Newton's second law. The net force applied onto a system is equal to the change in momentum over the change in time. So you can see the mathematical expression for Newton's second law, as well as the velocity update formula and the position update formula. Secondly, we need to understand gravitational force, which is the interaction which causes a mutual attraction between all things that have mass. As you see here, we have the written expression for gravitational force. M1 in this case is the mass of the star, and M2 is the mass of the black hole. So after manipulating it, we can isolate M2, and that's the equation for how we will find our mass using the gravitational force of the black hole. So first off, we did all of this in GlowScript. So some of our known conditions was that our delta T is going to be 86,400 seconds, which is 1 Earth day in seconds. We have the mass of our star, and we have our F net is going to be the Fg, or the gravitational force of the black hole. Then we solved for F net using the Newton's second law by doing change in momentum over change in time, as you see in this first area, and then at the bottom we would use our equation that we came up with to find the mass. So at this point we're going to have a bunch of different time points, and you'd have to calculate the mass individually at each point. So just to say what the mass is overall would be the average mass, and that's what it gave us in the computational code that we did on GlowScript. So now, moving on to part 2, don't crash. Just to reiterate, we're going to calculate the initial velocity of a spaceship in order for it to get close enough to the black hole without crashing and still being able to leave the system. And in order to do that, we'll get our necessary net forces and see how that works. So we did it again with a GlowScript model, just to model the trajectory of the spaceship. Initially, we put our initial conditions. We have the mass that we just calculated and other initial conditions, and then our initial velocity, which I will explain how we got there soon. Then we used, up here, we're just finding the different net forces. We have the net force on the planet, the net force on the spaceship, and then that will help us be able to find our velocity update and position update of both the planet and the ship. In order to find the initial velocity used, we just did some trial and error to try and find at which point is the spaceship close to the black hole but still able to leave the system. If it wasn't able to leave the system, this GlowScript model would say that it had crashed. So it was just trial and error. Our spaceship trajectory is the magenta line, so you can see it moving here. And then our cyan line is the planet orbiting the black hole. So some possible sources of error was that we had assumptions, so it's not necessarily applicable to real life because there's possible other forces in play that are acting on the spaceship or acting on the planet. So when we solved for our F nets, maybe it wasn't solely the gravitational force of the black hole acting on it. Additionally, we had trial and error, so our initial velocities were found simply by plugging in numbers and see which ones worked and see how close we can get. So it's not fully accurate in saying that this exact initial velocity is the closest possible thing you can get to then go around the black hole and still be able to get away. So just as for our discussion questions, what does it mean? So how is the net force and its perpendicular and parallel components different from the rate of change of momentum and its parallel and perpendicular components? So as we can see, they're mathematically the same, but the net force is the sum of all forces on a system, so you can find that by adding up all the forces. And our rate of change you can find by multiplying the mass of an object by the velocity, which can then give you your different components. So there's just different ways to get to the same answer. So for our last discussion question, we have the what if. What initial velocity would your spaceship have to be in order to enter some kind of orbit around the black hole? Now you also need to do this through trial and error and determine the speeds the same way we just did for the initial velocity, and that is what I did. Now this is my best attempt. It would be nicer if it was like a perfect circle, but we have an oval. So our magenta is the spaceship orbiting, and then again our cyan is the planet orbiting. So these were my speeds to get it to circle. Thank you. Here are the GlowScript links.